In this video, we're going to try to derive the time dilation formula we saw in the last video. So this is problem 37.1, page 58, volume 5. And so it's a little bit unusual, all these relativity problems are. So let's start with a bit of background here. We've got a spaceship that's traveling at some speed v. And so I'm going to call this frame S just because I needed the space to work here. And that is a frame that is at rest. So you can imagine you're just standing here and the spaceship goes flying by. So that's the frame that we're talking about here. You're at rest relative to the spaceship. The spaceship is moving with some speed v, all right? And now let's look over here. You can imagine a primed frame. Sometimes we'll call this the S prime frame or just the primed frame. And that frame is moving with the same speed as the spaceship in the same direction. And so what's going to happen here is this coordinate system is basically flying along with the spaceship. As such, in this frame, the spaceship doesn't move with time. Whereas in this one, when you're sitting at rest, the spaceship's going to move. So there's our two reference frames. We've got two events. So this is event 1. And that's in both frames. Event 1 is there's going to be a photon emitted, and I didn't draw it here, so let me do that. I'll talk about this in a minute. And so in this frame, that photon's going to basically travel straight up, and then here we have event 2. The photon returns to the bottom. Just making sure that's visible, it is. So that's the same event over here. Now, think about this. In this frame, if we see the photon going straight up, hitting the mirror and bouncing straight back, that means it must actually be kind of going at an angle, because if this event is observed in both frames, right, if this photon goes straight up, it's not going to end up being, right, it would go straight up and then straight back down, and it wouldn't hit the floor over here. So in this one, this is why I kind of delayed this. I want you to imagine, let's kind of visualize this here. The photon's actually going to take a path sort of like this. I marked the halfway point right about there. Oops, that's sloppy. Okay, so the photon's actually going to be coming off here at some weird angle like this, because then it's traveling with speed c, but the spaceship's traveling really fast, right? So it's traveling so fast that the light has to be angled in order to hit the mirror and bounce back down and hit the floor right there. Okay, so that's what's going on in this situation here. Great. So let's read the question now. I'm looking at the question. It says, the photon travels distance 2d in frame S prime. So in frame S prime, right, this thing just goes up and back. That distance is d, where d is the distance between the bottom and the top. If you're curious, this is sometimes called a light clock, where these photons are bouncing. You'll put a mirror on the bottom. They call these light clocks, right? And all right, whatever. Anyways, great. Now, what is the question asking for? Determine the distance traveled in frame S. So notice this dashed blue line is describing the distance it's traveled. So maybe what I'll do is I'll just call this length, well, let's just look at this. I think we can see a triangle here. This side of the triangle is D, and I'm going to call this side of the triangle L for a minute. So that means this side of the triangle is L squared plus D squared. Great. Now, what is L? Well, let's think about it. We know this ship is traveling with speed v, And then what I'm just going to do is I'm going to write down the distance traveled in terms of this unusual time, delta t. So that's going to be, that's half of the time, so this would be 1/2 v delta t. And I believe that's what I wanted to write this down. Yeah, so we're trying to find the distance traveled in terms of d, v, and delta t. So this gets the v and the delta t involved. Now watch, look out carefully here. Notice on this side, the times are t prime, the x's are x primes, the final time is delta t prime. We do not necessarily think delta t prime should be the same as delta t. Okay, so just be aware of that. So then in this case, the distance traveled in frame S, sometimes called the unprimed frame. So you got the primed frame, S prime, and the unprimed frame, S. The distance traveled in the unprimed frame, S, is going to be 2 times the square root of L squared plus D squared. And even though this seems a little bit odd, I'm going to bring that 2 inside because I can see it's going to cancel this fraction. So this is actually the square root of 2L quantity squared plus 2D quantity squared. Take a second to believe that, right? When this comes in, it's a 4, and then I can bring it inside the squared by square rooting it again. So again, this would be 4L squared, which is the same as 2L quantity squared, etc. Same for D. Now let's get this involved, and notice we can get rid of that factor there. So it's going to be what? The square root of V times delta T quantity squared plus 2D quantity squared, and that is the distance requested. That's part A. Part B. Light travels, okay, well, let's just mention this here. Look, in this frame, according to special relativity, the speed of light is the same in every frame. So the speed of this photon has to be c. The speed of this photon in this frame, it's still going to be c, right? You don't pick up some extra, right? You don't get an extra boost from the rocket moving at some speed v. It's still going to be emitted and still travel at the speed of light. Okay, so the old velocity addition rules don't apply. For the speed of light, it's c. So notice over here, well, how far does this thing travel? 2d. Well, isn't that c times delta t prime, how many meters per second times the time interval, should equal 2d. Okay, that seems reasonable. So now our question is, I want to relate that to this term. Well, I know similarly, this should be c times delta t with no primes. So again, c times delta t prime gives me this distance. Well, this distance should be c times delta t, right? Because it was traveling along this line at that rate. Okay, that's cool. So now part B asks, determine a relationship between the primed time and the unprimed time that doesn't involve D, right? So what we're looking at is, right, you could use this thing as a clock, but every clock's going to have a slightly different size. Our goal is to get a relationship between delta T prime and delta T that doesn't involve this distance. And the key here is to do this step. I can see that 2D relates to the primed frame, and that's how I can get this relationship started. So once we get to this step, it's just algebra. I'm going to go ahead and do some of that algebra, but I'm going to do it over on the other board. So let's do that. And if you want, you could pause the video and try and race me or whatever you want. I'm just going to get this. So B. and we found and then the very first step, we replace this using that interesting result from the primed frame, that's C delta T prime squared. Making sure that's on the board. Okay, so now I get, go ahead and race me. Maybe I'll keep that one in blue. So I'm just going to square both sides. Okay. And so now I guess it makes sense maybe to write all of these the same way. V squared delta T squared plus C squared delta T prime squared equals C squared delta T squared. All right, group the T's here, so it looks like, I don't know, how about we move this one over there? So I'm going to get going to check. When I bring this term over, I can factor out and I get a C squared minus V squared. That's good. And so then maybe what I'll do now is solve for delta T. I guess maybe what we'll do is, you know what, I'll move that one over here. I'll move this over here. So I get lots of different ways to do this. And this one, I'm just dividing over here. And now I see, couldn't I just take every term and divide it by C squared? That looks kind of nice. So notice what I'm left with. On the numerator, 1 minus beta squared. Like that. Oh, squared. And lo and behold, I can see gamma popping out here. If I bring this up here, what do I get? I get delta T equals delta T prime times gamma, where gamma is 1 over the square root of 1 minus beta squared, with beta equals V over C. Take a second, make sure you actually see that. Right, when I square root, I get rid of these squareds, but this gets a square root of that whole thing. The square root of the top is just 1, so it's the square root of this, and beta is V over C. So this does work out. Well, isn't that our time dilation formula? Let's think. In this case, let's go back to the pictures and talk about proper time and all that. Okay, so in this case, the photon leaving and the photon returning were measured at the same point in space. That means this is measuring the proper time. So delta T prime should be the proper time. Okay, so this one, and I'm just, review the last video if you don't remember that. Proper time, both measurements take place at the same point in space, the same position. Okay, so this is the proper, we'll just say S prime measures proper time. Great. Now in this case, this other time ends up being a little bit longer. How do I know? We just found that delta T was equal to delta T prime times gamma. Oh man, this color choice was really bad. Let me write it like this. We found delta t, the time in the purple frame, was equal to, oh my gosh, delta t prime. I apologize for the color coding. But so in this purple frame, that was the unprimed. And then over here, there was a gamma. That was what we found. And notice, gamma is always greater than 1. So we see that this time will be shorter than all other times. Said another way, the moving clocks run slowly and record longer time intervals. Gamma is bigger than 1. Every other time interval recorded will seem longer. So your clocks must feel like they're running slow. All right, and then what's part C? Assume the clock in S frame requires exactly twice as long to complete 1 tick. Determine the speed of the rocket. So let's go back over to here. Come on. And then I'm going to try and redo this coloring here. Oh, whatever. Let's just do this one right here. What did we find? We said that delta t, this was in frame S, at rest relative to ship, was equal to gamma delta t prime. This was frame S prime, ship at rest in this frame. You could say it this way, this was the moving frame. So in the moving frame, right, the ship is at rest. All right, so in this case, we were told delta t is equal to 2 delta t prime. If you read the wording of the question, it says, assume the clock in frame S requires exactly twice as long for the clock to complete 1 tick. Determine the speed. Well, hopefully what you can see here is that gamma equals 2. So now, let's write this in. 1 over the square root of 1 minus beta squared. You're going to do this a lot. Equals 2. Square both sides. 1 over 1 minus beta squared equals 4. Cross multiply. 1/4 equals 1 minus beta squared. And then keep going. What do we see? Let's move the beta here and the 1/4 there. Beta squared equals 1 minus 1/4. Beta equals the square root of 3/4 equals the square root of 3 over 2, which most of you probably know is 0.866. Right? It's the square root or sine or something of whatever it is, 60 degrees. All right, I don't know what the next digit is. I don't really care. But so notice, remember, what does beta mean? Whoops. It means the speed is 0.866 c, meaning 87% the speed of light, or 86.6% the speed of light. All right, so a lot of times we'll answer our questions in this form like that. And I think that's enough on this question.